Hello! In this video we will revisit the block on a ramp problem, but this time we will assume that there is friction between the two objects, which is the case for most materials. We will ask two questions. First, when the block is already moving, what acceleration does it feel? Second, when the block is not yet moving, how can we get it to move? First, let's start by adding the frictional force to our diagram. Since the block will either be moving down the hill or trying to move down the hill, the frictional force is going to point up the hill. The magnitude of the frictional force is mu times the normal force, where mu is a frictional constant that depends on the materials involved, and typically ranges between 0 and 1. Let's assume that we know what mu is. So, first thing we should probably do is figure out what exactly the normal force is. Now, the normal force is going to be whatever it takes to cancel the perpendicular force of gravity, since that is the force that is trying to push into the surface of the ramp. That means the normal force has the same magnitude as the perpendicular component of the gravity force. So let's figure out what the perpendicular component is. Well, the perpendicular component is adjacent to theta, and we know that the hypotenuse is mg. So let's use the cosine relationship, which says that cosine of an angle equals the adjacent over the hypotenuse. In our case, that means that cosine theta equals the perpendicular component of gravity divided by mg. Solving for the perpendicular, we get that it equals mg times cosine theta. Now, let's recall that friction works differently depending on whether or not the object is already moving. Let's start with a case where the object is moving, called the kinetic case. Our goal is to find what the acceleration of the object is, because that will tell us how it will move. In the kinetic case, the friction just has a fixed value, that is equal to mu sub k times the normal force. Mu sub k is the coefficient of kinetic friction, which is a somewhat lower value than the static friction value, which we will use later. Since we know what the normal force is, we can actually write the frictional force as this. Now let's write out the F equals ma equation along the slope. The sum of forces is mg sine theta minus the frictional force. Again, we chose down the slope to be positive, so that's why mg sine theta is positive, but friction is negative. The sum of forces along the slope equals the mass times the acceleration along the slope. Mass everywhere cancels, and we are left with this expression for acceleration. Great! That is what we were trying to solve for. Notice that the mass of the object plays no role in its acceleration. Next, let's examine the static friction case, which is when the object is not yet moving. Our diagram looks mostly the same. We need to recall how static friction works, though. The force of static friction will equal whatever will prevent the object from moving, which means keeping the acceleration to 0, which means matching the forces trying to accelerate it. However, it has a maximum force value of mu sub s times the normal force. Mu sub s is the friction coefficient for the static case, which is usually higher than the mu sub k for the kinetic case. If the force trying to move the object exceeds this maximum force, even by the teensiest little bit, then the object will start moving, and it enters the kinetic friction case. Therefore, our question in the static case can't be, what is the acceleration? We know that the acceleration is 0, and if it isn't, then we are in the kinetic case. So our question should really be, how can we get the object to move and leave the static case? That means we want to know the point at which the force trying to move the object just barely exceeds the maximum static friction force. So we can write this inequality, where the downhill pull of gravity is greater than the uphill resistance of the static friction. Immediately we see that there is an mg term on both sides, so those cancel. So the only factors at play are the angle of the hill and the coefficient of friction. So let's just get each of those factors on their own side of the inequality. By the way, sine over cosine equals tangent, so we can write this. This says that if the tangent of theta is greater than the static friction coefficient, then the box will start to move. If we wanted to know what that angle actually is, we can apply the inverse tangent function to both sides of the inequality, which gets rid of the tangent on the left side and turns the right side into the inverse tangent of mu sub k. Any calculator or computer has an inverse tangent function that you can use. Great, so now we know what angle we need to tilt the hill at in order to get an object to start moving. That's it for this video. Thanks for watching.